Here's another impulse momentum diagram we're going to draw. We want to find a speed of something, right, immediately after impact, right, at a certain time, and the time it takes for something to slide. We've got car B up there that can slide on the flat car C, right, and there's some friction going on with that, but a little bit different here. We've got two things that hit each other, but then they bounce apart. So it says right there, instead of coupling, which would mean they join and then have the same velocity, here they bounce apart. So they do not have the same velocity on the other side of the impact. So let's do this. Let's do we're going to want to talk about the coefficient of restitution and the speed of cart C down there. So let's draw an impulse momentum diagram for the two cars when they hit, and then afterwards, now they will be separated again. So let's see what we've got. The flat car is at rest, so that has no velocity. I've got here the mass of A times the velocity of A, which we're told is 6.5 kilometers per hour. Right? Across the impact, right, these things are going to hit each other. So there's going to be a big force right there, F delta T, F delta T. Also, we're going to have the weight times delta T of car A. We're going to have normal forces. We're going to have normal forces for the other. We're also going to have its weight. And interestingly enough, we're going to end up with a force of friction times dt from car B. And that should get us, we'll also have a normal force from B times delta T. And then afterwards, we've got now the mass of car A. And we're told that it has a speed after impact. It rebounds. So that means it'll be going in the other direction. And now car C is going to have some velocity then after. So often we use the prime to do after impact. So if we throw our coordinate system on, there's our x, y. And now we're in the summing linear momentum business. And as we kind of look at our diagram here, obviously the big red arrows are equal and opposite, so there's no contribution. We would end up with an equation that looked like MA times 6.5. And now notice on the impulse, we've got a force of friction times delta T. We're going to neglect that for two reasons. One, the force of friction is not an impulsive load. And again, this delta T is small. So compared to the forces of impact, right, that force of friction is going to end up being very small. You can think of it as, right, it's a static load. And so it really doesn't care what delta T is. Those arrows, right, F is going to be proportional to delta T. So as delta T gets smaller, F has to get bigger because the force of impact is again going to be constant across the collision. And so on the other side, we're going to have a minus MA times 2 plus MC times VC prime. So that gives us the ability to solve for VC prime. And you're also asked for the coefficient of restitution. Right? Coefficient of restitution is also known as the relative velocity equation. And the way you can think of this as velocity after of particle A minus the velocity after of particle B divided by the exact opposite on the bottom. It's going to be B minus A. So if we just go ahead and apply to our situation here, we've got for velocity of A after sitting right there. Now this is a vector equation, so that's going to be a minus 2 because it would be going in the negative x direction. I've got the velocity after for the other particle, which for us is the cart C. So that's going to be minus VC prime. On the bottom, we're going to have the exact opposite. So we would have the initial velocity, which would be 0. And then we're going to subtract the velocity of A, which is initially going in the positive x direction. So that would be 6.5. And so we would take our answer from part 1 right there and just go ahead and plug it in right there to find the coefficient of restitution. Now in part B, we're asked to find the time it takes the load to slide to a stop. So our impulse is going to be the force of friction. And we would know that the force of friction is going to act over a decent amount of time. So this would be delta t is not going to be short. So it's not going to be an impact. What we've got now, we're going to look at just before it starts to slide, which is at the beginning. It's going to be our answer from above up there. It's going to be the velocity after rebound. That's going to initiate the slide from above. So this is going to be mvc prime, right, from above, from the answer above. So I'm just going to draw an arrow to that right there. I've got then to go across the slide. So this thing is moving. It's going to be, again, over some time, right? I've got all my weights. I've got normal forces, right, which I would have to integrate. I'd have a weight right there, right? My impulse force, again, is internal, right? That force of friction is occurring. It's acting equally on the weight above and the weight below. And then after, I'm going to end up with this thing stopped. So at some location, the sliding is stopped. And now I've got both masses, mc plus mb. And that's going to be at the velocity bc prime. All right, so again, I'll label these as some f delta t, f delta t. And so there's our impulse momentum diagram. And so I just got to put a coordinate system on there. And now I can sum momentum in the x direction. So that'll give me the velocity, obviously, right? This will give me the ability. We've got a known there. Nothing comes out of that diagram. And on the other side, we've got the masses times v bc prime. So that'll give us the ability to solve for v bc prime. But it doesn't give us the answer for how long it takes. Right? The answer for how we're going to find that is sitting on one of those red arrows. And so we need to expose a red arrow. So what I'm going to do now is just draw an impulse momentum just for block B. And so we'll just kind of fill this in. We've got 0 at the start, right? It hasn't begun to slide yet. I've got, right, the weight times delta t. I've got some normal force times delta t. And now I've exposed the force of friction times delta t. I can find the force of friction from an FBD KD. We would know that's mu k times n. And then afterwards, I would have a velocity or momentum mass of b times vbc prime. So as we look at linear momentum in the x direction, again, not being hasty with our coordinate system. So if I sum linear momentum in the x direction, right, that is now active. And again, because I know the force of friction, because again it's calculated statically, and now I've got the ability to solve for delta t, because again I know this because I solved for it with the whole system. We'll continue with some impulse momentum diagrams. A new addition to these is a coefficient of restitution, E, which is going to be a velocity after divided by a velocity before impact. And so these are going to be velocity differentials, so we will end up laying that out in class. But let's go ahead and take a look at these two balls. They're frictionless, and again that's going to mean that the impact force is going to be in the directly in the normal direction to contact. So let's just kind of look at drawing these real big here. We're going to need to grab some components. So then I will add in the impact diagram, and then we'll have a picture after. So let's go ahead and again align some things up here. Let me take you back to the picture up there. So we're going to set up an axis system here where we put a tangential, right, perpendicular to the line of impact. I'm going to put then a normal direction right along that line of impact. So on each of these diagrams, we've got a tangential and a normal. So I'm just going to go ahead and put them on each just to help us with the geometry here. And then also down here we'll have a tangential and a normal. So let's just go ahead and say right before impact, right before we end up with the mass of A times the velocity of A, and we have some geometry here of 40 degrees. All right, we also have, again, momentum wise, so this is going to be the mass of B times the velocity of B, and we are told that that angle right there is 25 degrees. So I'm going to spend just a few minutes right here, and I am going to draw some components in there. I'm going to draw them in the normal and the tangential directions. Same thing here, and then also in the normal direction. So we're kind of oriented there. Right? These two particles connect with each other. Right? There's our big impact, right? F delta T, F delta T, because it's frictionless. It's going to be right along that perpendicular axes to the contact. After, right, we've got quite a bit of unknowns going on here. So after the impact, I basically don't know any of the velocities, so I just need to draw that picture-wise using the coordinates that we've got. So what I'm going to do is call this MA, velocity prime for A in the tangential. This is going to be MA, velocity A after in the normal direction. And again, at this point, I really can't be wrong in what I draw here. I just need to represent the fact that I do not know what the velocity is. So I've got the tangential direction for B after collision, that's what the prime means, and I've got the mass, and I've got a B normal direction. And so what we end up applying in class is, right over here, if we look at this, we've got lots of unknowns here. Turns out we know the velocities before, but as it sits right over here, we would have 4 unknown velocity components. And so what our analysis is going to bring us to is we are going to look in the tangential direction, we're going to find that momentum is conserved. And then in the normal direction, in the tangential, we're going to do it for each particle individually. In the normal direction, we're going to do both together. Right, that puts that impact force, right, as an internal force, and we end up then using a coefficient of restitution. So we end up using an E equation, and that would say that the velocity of B is going to turn out to be in the normal direction after, with the velocity of A after divided by, and we just got to change the direction here for before. Talk about that in class. But if I do B over A, then it's got to be A minus B. Sorry, if I do B minus A on top, it's got to be A minus B on the bottom. All right, in this example, we're going to draw impulse momentum diagrams, but we've got a particle that's not free. Right, it's connected by a cord there, and so that's going to have a implication here as we do our impulse momentum diagram. So let's go ahead and look at our system together right before impact. We'll then look at that thing right as it impacts. And then afterwards, those things are somehow going to be separated. Right, so again, that's kind of the new thing that we've got here, right, is that things aren't sticking together, but that they are bouncing off each other. So let's go ahead and look at our 20 degrees everywhere. So coming down for momentum before, I've got the mass of A times VA. Right, and I'm also going to, again, create a coordinate system here that would be tangential. I'll go ahead and put normal along the contact direction. So I'm going to kind of do this in all of them. And again, same thing here. I've got tangential and this normal direction. So right before impact, I've just got momentum in block A. As they hit each other, we get our infamous force, right, our F delta T, F delta T. But we have to include another very important force. We have an external force to the system, which is supplied by the tension in that rope. And what's going to happen is that force, right, is going to be activated by the collision. So it's different than a static force. There is a tension, right, in a static sense, but when that block hits the other block, that tension is going to increase. And kind of remember, just like we had the guy that fell off the construction worker, fell off the girder, and talked about the tension in that cable. So the same thing is happening here. We're going to have an impulsive force in that tension in the cable. So we've got afterwards, right, after the impact, we've got the mass of A times VA prime for after. And we've got something that has circular motion. So I know that the velocity of B is going to be horizontal, and therefore the momentum is mb times v. So we've got all of our components set up. And so when we analyze the system together, all right, we're going to have to take care when we sum linear momentum, right, we're going to have to end up doing it in a horizontal direction so that we can avoid that force. Right? That's not an internal force, but an external force to the system. So there's a couple things that we would need here. We're going to need a E value because we've got two objects that are hitting and bouncing off each other. And then the other thing it asks for is an impulse during the impact. So how do we get to this force in here? Either one of those forces will work. And so the cleanest way to do it, to again avoid that external force, is I'm just going to look now at block A on its own. And so at this point we would again have all these MAVA prime, and I would end up with, there's my impulsive force F delta T, and up here I've got MAVA. Alright, and again, just to kind of finish that up, right, we also have normal force, and we have a weight that's sitting on there times delta T. And again, those static forces are going to be negligible because of the delta T. So the same thing would occur down here, the weight times delta T, and the normal force times delta T would be excluded because their effect would be much, much smaller than the impulsive force sitting right there. So we would just end up now, again, doing some linear momentum in the normal direction, and we'd then be able to go solve for that. So our last one, we have an interesting concept question here. We've got two particles before and after collision, and it asks, is it even possible for this to happen? So why don't we go ahead and do impulse momentum, because we've got a collision. So let's go ahead and look at A and B, and then they're going to connect with each other, and then they're going to bounce off each other. So again, we should be active to this coefficient of restitution when something like that happens, when something doesn't stick together. Right, we've got multiple possible velocities over there. So let's go ahead and look here. We've got the mass of A times V, and we're told that the mass of A is 5. So we've got 5V. Here I've got at impact, right, there's our big F delta T, F delta T. After impact, I end up with mass of B times 5V. I'm told the mass is 1, so I end up with 5V on the other side. So if we sum linear momentum in the x direction, we can go ahead and call that way positive. I'd end up with 5V plus 0 equals 5V. So the system passes the impulse momentum. But we've got one more thing to check, and that we've got a coefficient of restitution that has to be examined here. So we know that that is the velocity after of one of the particles minus the other. In whatever order I do it, then I have to do it in the other order on the bottom. So if we look at the velocity after of B, that's going to be 5V minus 0. On the front side, the velocity of A is V, the velocity of B is 0. And so I end up with a coefficient of restitution of 5. And we then have to remember that the coefficient of restitution has to be between 0 and 1, which is elastic. So this is highly illegal.